For as long as I remember, I've always wanted to build a device that can shoot massive bolts of lightning in my own home. I'm not strange. And spoiler alert, I did it! I'm a success! But the journey to get to this point took almost 2 years and it nearly broke me. So before I get carried away, we need to go back to the beginning. There are actually a lot of ways to make high voltage electrical arcs, but the one that's always been my favorite is the Tesla coil. Specifically, the Tesla coil that I wanted to build was a QCW DRSSTC. What? Okay, I think I'm gonna need to break this down. Forget about everything except for the TC part. TC just stands for Tesla coil, and a Tesla coil at its core is just a weird transformer. It has 3 main parts. First, there's the secondary coil, which is typically a long cylindrical coil with often over 1,000 turns. Then there's the primary coil, which is located around the base of the secondary coil, and it has much fewer windings, sometimes as little as 2 or 3. Then there's the top load. The top load is basically like one plate of a capacitor, where the other plate is the ground. Like literally the ground. Now the capacitance of the top load is very small, but in combination with the secondary coil, it forms a resonant circuit. When an alternating current at exactly the resonant frequency of the secondary circuit passes through the primary coil, massive voltages are generated at the breakout point. And these voltages are so huge that arcs can break out even though there's no grounded objects nearby. Now we can add in the SS part. SS stands for solid state, and it refers to how we generate the signal that flows into the primary coil. In a solid state Tesla coil, we use transistors, which are arranged in a configuration known as an H-bridge. This H-bridge switches like this, so that it creates a signal that goes between plus and minus V bus. Each of these switches has a gate, and these gates are controlled by a driver. The driver is responsible for a couple of things. As mentioned before, it generates the signals which control the H-bridge, but it also takes in an interrupter input. The interrupter controls when the Tesla coil is on, and typically it produces short pulses which range from a few microseconds to a few milliseconds. This is needed to keep the average power of the Tesla coil pretty low while keeping the peak power high. In other words, it stops the Tesla coil from exploding. Most Tesla coils are interrupted, and that's why you see them make bursts of lightning instead of a kind of fluff of plasma that they would make if they were continuous. Drivers also take in feedback. In SSTCs, feedback is taken from the secondary coil either through an antenna or a current transformer. Feedback is used to lock in exactly on the resonant frequency of the Tesla coil so that the voltages generated can be as high as possible. In a DRSSTC, we add a capacitor in series with the primary coil. This forms a second resonant circuit. The capacitance and inductance of the primary tank circuit, as it's commonly referred to, are carefully chosen so that they resonate at the exact same frequency as the secondary coil. Instead of taking feedback from the secondary coil, we now take it from the primary resonant circuit. Now that the primary coil has essentially no impedance, massive currents can flow as more power is dumped into the tank circuit on every oscillation. And this is where we start to get into big lightning territory. Now the problem becomes these currents can become so high that they actually damage the transistors. So we add an extra current transformer that monitors the current flowing through the primary circuit, and if it goes above a set threshold, the driver will cut off the oscillation. This type of circuit is known as overcurrent detection, or OCD for short, not to be confused with the mental disorder. So by now you've probably noticed the correlation between the number of letters in the Tesla coil acronym and the complexity of the design. Unfortunately, this function is actually exponential, and you'll see why as we come to the final part, QCW. So QCW stands for quasi-continuous waveform, and it's kind of a weird name. It's really not self-explanatory. So far, we've been assuming that the Tesla coil interrupt signal is purely digital, so either the Tesla coil is 100% on or 100% off. But in QCW, this value ranges from 0% to 100%, so that the output power of the Tesla coil can be modulated. Let's not worry about how this can be done yet, we'll get to that later. Now, instead of powering the Tesla coil at 100% power right away, in QCW, we slowly ramp it from 0% to 100% over the course of a few milliseconds. This causes the arc to preferentially grow in one straight path with minimal branching instead of a whole bunch of branches like before. So what we've done with this is not made the arc longer, but instead taken all of the small branches and put them in one straight path. QCW DRS's TCs can often produce arcs longer than 2 meters from a secondary coil that's just a tenth that length. So TLDR, QCW DRS's TCs make massive lightning, but their big downside is that they're super complicated and definitely not for beginners. So now is probably a good time for me to mention that I've never made a working Tesla coil before. About 4 months after I finished my plasma toroid project, which was 2 years ago now, and when I looked like this,
Plasma toroid isn't working.
I tried to build an SSTC, and no matter what I did, I couldn't get it to work. So eventually I kind of just gave up on it. And about 4 months after that, I started working on this project. So that's how long it's been. But there's still one more thing, and that is, well, how do you actually modulate the output power of the Tesla coil? The easiest way is pretty intuitively to actually just modulate the input voltage to the H-bridge. Since current has a pretty linear relationship with voltage, this will control how much current flows through the primary coil, and as a result, how much power the Tesla coil actually outputs. And the circuitry to do this is also actually pretty simple. All you need is a transistor to chop up the input voltage, and then a filter to smooth out that PWM. But I don't actually like this approach, and here's why. Since the currents that the H-bridge draws are huge, you need massive components that can filter out the PWM and not saturate. This means that especially the inductor needs to have a huge core with low magnetic permeability, but still high inductance. And this combo, it actually just means expensive. And that's along with all the other power electronics, which are also super expensive. And I want to minimize spending on this project. We'll see how that pans out. Spoiler, bad. So instead, the approach that I'm going to be using is called phase shifting. It doesn't require any extra power electronics, and it just changes how we drive the H-bridge. To illustrate how it works, we need to change our perspective. The top two waveforms here are the voltages at either end of the H-bridge, and these are commonly referred to as half bridges. You can see that they're opposite each other, or 180 degrees out of phase. You'll see why that interpretation is important later. The bottom waveform is the voltage difference between these two half bridges, and this is actually what the primary coil is experiencing. Here's the trick. We can shift the phase of one of the half bridges so that now the H-bridge is only sending power to the primary circuit for a percentage of each oscillation. This percentage is dictated by the amount of phase shift between the two half bridges. A 0 degree phase shift would mean a 0% power transfer to the primary circuit. Since the voltages are always the same, there will never be any voltage difference between the two half bridges. A 90 degree phase shift means 50% power transfer, and then 180 degrees phase shift means 100% power transfer. And that's returning to how it was before we shifted the phase and how the half bridge normally operates. The big downside of phase shifting is that now one of the half bridges is switching out of phase with the primary current. This leads to hard switching, which happens when there's still current flowing through the switch while it changes states. This is bad for transistors, and it causes extra heating and can shorten their lifespan. Even with this downside, I still like phase shifting better because it's more elegant and it cuts down on power electronics, which are typically pretty expensive. So I decided that my first big step would be looking for a driver capable of phase shifting. And after looking around for a really long time, I couldn't actually really find one. Either the design was kept secret by the person who made it, or it was way too complicated for me to assemble with the equipment that I had. So after a while of looking around and not finding anything promising, I decided that I would actually just design my own driver from scratch. Right off the bat, I decided that my driver would be based around a CPLD. CPLDs are a kind of programmable logic device, and unlike computers, they don't operate based off of instructions that are executed one after the other. Instead, you program logic circuits, which are composed of latches and gates and don't have a fixed timing. Tesla coil drivers rely on a lot of fast signal conditioning, and this is typically achieved just by wiring together primitive logic ICs. For example, one of the most famous Tesla coil drivers, the UD2.7C, only uses 3 individual logic ICs. But since I knew that my driver would need a lot of complex logic circuitry to be able to support phase shifting, I decided it would just be easier to throw it all into one chip that I could program later. After a bit of searching on DigiKey, I found this CPLD, which was cheap and it had more than enough I/O. The only thing that's a little bit annoying about it is that it isn't 5 volt tolerant, so I'll have to make sure that all the signals feeding into it are less than 4 volts. I used pretty standard feedback OCD and gate drive circuits, which were all based off of or direct copies of the circuits used in the UD2.7C. There were also some voltage regulators and a couple of analog circuits that couldn't be fit into the CPLD because of its digital nature that I placed around. The only circuit left was the phase shifter. The phase shift circuitry that I decided to use was based off of the simple driver, and here's how it works. Firstly, this signal generates a saw wave with a period double the feedback frequency. The interrupt signal is generated by an external interrupter, and it's coupled through a fiber optic cable to avoid electromagnetic interference that is generated by the Tesla coil. The receiver receives a digital PWM signal that's generated by the interrupter, and this signal contains the QCW ramp. This signal is smoothed out into an analog voltage, and a comparator is used to detect the analog signal and generate a digital interrupt signal so that the driver knows when to start and stop oscillating. The analog signal is then compared with a saw wave, and it's important to note that while the interrupt signal is on the order of tens of milliseconds, the feedback signal has a period of a couple of microseconds, so at the timescale of the feedback signal, the analog ramp looks like a flat voltage. Every time the saw wave goes above the analog voltage, a flip-flop is toggled, and this creates a square wave with the original frequency, but a phase shift dependent on the analog voltage generated by the interrupter. As this analog voltage increases, the phase shift becomes greater with a maximum phase shift of 180 degrees. This is exactly the range we need for phase shift modulation. With all of this in place, I routed the board and ordered it. 2 weeks later they arrived and they were looking really good, so I assembled one. I'm only placing components on the low power side of the driver because I expect this to be where there are issues and it allows me to save a little bit of time. The CPLD has an extremely small pin pitch, and after I reflowed it, there were some solder bridges that I had to clean up. Once assembly was complete, I connected the board to a power supply and immediately there was a short circuit, and the 3.3 volt regulator was very hot. So after taking a closer look at the pinout of the regulator, I realized that it was completely wrong, and I basically instantly destroyed it. So I ordered the new boards with the correct pinout, and while I was waiting for them to arrive, I tested some of the analog circuits and they all seemed to be working, so at least that was encouraging. The version 1.1 boards arrived and I quickly assembled one. It didn't seem to have any critical flaws, so I moved on to trying to program the onboard CPLD. Oh, wait, did it actually work? And I was actually able to program it, so that was a huge relief. I'm actually so happy right now. After that, I started writing out the logic in a hardware description language known as Verilog HDL. It was going pretty well, and after a few days, I had the bulk of the logic figured out. There were a few minor issues with the board that I won't bore you with, but they all mostly just involved changing some component values and were relatively easy to fix when I made the next revision of the board. The version 1.2 boards arrived, and this time I was feeling confident enough to fully assemble one. Now the only thing that I needed was a Tesla coil so that I could actually test to see if it worked. Shoot, there's paper on my foot. Let's talk geometry, specifically Tesla coil geometry. QCW DRSSTCs are quite unique from normal DRSSTCs because they operate with a resonant frequency that's much higher, typically 300 to 500 kilohertz. They also operate with a much longer interrupt duration that's typically on the order of tens of milliseconds instead of a fraction of a millisecond, like in a normal DRSSTC. These differences are needed to make the QCW ramp as effective as possible, but it also results in them having a really unique shape. The secondary coil needs to be small enough to have a high resonant frequency, and actually, because of my old SSTC project, I had a secondary coil that fit this requirement perfectly. It resonated around 380 kHz with the top load, and it had a good form factor. The primary coil in QCW DRSSTCs is quite unique. It has a large number of turns close to the secondary coil, and this increases coupling and allows for better power transfer. But it also results in the primary coil having a high impedance, and this limits the resonant current during operation. This is actually a good thing because it allows for longer interrupt periods without exploding the H-bridge. I didn't record myself building it, but this is what I came up with. The primary resonant capacitor was a bit tricky, and this is because it needs to be able to handle high resonant currents. Typically, people chain together a whole bunch of small film capacitors, but I'm lazy, so I decided to just use Soviet military surplus. But actually though, ceramic doorknob capacitors are basically designed for this purpose, and it just so happens to be that there are a lot left over after the USSR collapsed. So you can actually just buy them on eBay for pretty cheap, and I bought 2 of them, and together they make a 9.4 nanofarad 10 kilovolt capacitor bank. The last thing I needed was the H-bridge. I decided to design my own, and it had some questionable layout choices. The PCB mounts onto a heatsink, and then on top I kind of just hot glued the gate drive transformers. These are used to galvanically isolate the driver from the H-bridge, and they also step down the drive voltage a little bit. I didn't mention them before because they're kind of just a small detail. With all of the major components of the Tesla coil now in my possession, I connected everything up and connected the H-bridge to a 40-volt power supply for a small test. And it actually worked. There were some small arcs shooting out of the breakout point. But weirdly, the driver kept bugging out, especially when the interrupt period was longer than 1 millisecond. And on one of the runs, the driver wouldn't stop oscillating, and then it fried 2 of the transistors.
That doesn't sound good.
I think this was being caused by electromagnetic interference, so when the new transistors arrived and I replaced them, I also made a shielded case for the driver. The interrupter PCB also arrived, so now I could use a purpose-built interrupter instead of a function generator connected to a fiber optic transmitter like before. This also meant that I could send QCW ramps to the driver and potentially test phase shifting. I connected everything together again, and the Tesla coil still worked. I was also able to test out some more systems, like OCD, and they all seem to be working too. I think that electromagnetic interference was definitely the culprit of the weird behavior that was happening before. I was feeling confident enough to try powering the Tesla coil at 60 volts with a 5 millisecond interrupt period. This was pushing the Tesla coil way farther than I had before, so I was a little bit nervous. But everything still worked! So now I was feeling ready enough to test phase shifting. Using a current transformer to measure the current across the primary during an interrupt period, I was able to clearly see a ramp in current, and this current ramp matched the ramp that was generated by the interrupter. So this showed me that the phase shifter must have been working. Using a QCW ramp, the arcs on the Tesla coil output were now clearly pretty different from how they were before, and they were much quieter and much straighter, which is exactly what we expect from QCW, so this double confirmed that everything was working. Now the only limiting factor was the input voltage to the H-bridge. If I wanted higher primary currents to make larger arcs, then I would need to increase the voltage feeding into the H-bridge. But before I could feel comfortable doing that though, I wanted to put everything in a housing. That way the electronics could be securely attached instead of just sprawled out all over a table, which is a safety hazard. For the new power supply, I used a variac to control the voltage of the AC mains, and then connected that to a full bridge rectifier to rectify the AC, and then fed that into a big bus capacitor. I should probably actually do a note on safety here. Now that we're working with AC mains, a lot of stuff can go wrong. First, it's really important that the bus capacitor have a bleed resistor on it, otherwise it can stay charged with a dangerously high voltage for a really long time, waiting for somebody to touch it and then get messed up. The bleed resistor will slowly discharge the capacitor over the course of like 10 minutes, but as a general rule of thumb, I won't go poking around the Tesla coil for at least 15 minutes after running it. The other thing you might be worried about is what if an arc hits me? And yes, in some Tesla coils this would be really dangerous, but because the frequency of the arcs in my Tesla coil are around 400 kilohertz, they actually can't really stimulate nerve cells at all, so the current just passes straight through your body. This doesn't mean it's safe though, because these currents are still quite high, and sometimes they can be above 1 amp. The current goes straight through your body, and it can burn you, but it doesn't stimulate nerve cells because of the frequency. But since these arcs last for such a short period of time, and they're quite intermittent, it would take a really long time for your tissue to heat up enough to get 3rd-degree burns. So, it's kind of safe for you to touch it at least once as long as you don't have a pacemaker or something, but it wouldn't be a good idea to make a habit of it. As a general rule of thumb, don't listen to some stupid kid on the internet, do your own research. But also, unless you're really confident about your electronics knowledge, don't replicate anything I'm doing past this point. Because even though the arcs might be kind of safe, the mains electricity involved in this stuff is not safe at all and could really hurt you. Anyways, if you're wondering why I skipped past building the housing, it's mostly because I forgot to film any of it. Moving on! Before powering the Tesla coil from the mains, I switched it back into normal DRS-STC mode because, as I mentioned before, phase shifting adds a lot of extra stress on the H-bridge, and I was a little bit worried about it exploding with the new much higher input voltage. So with everything set up, I started turning up the variac. I set the OCD pretty conservatively on this run, so once the variac turned to around 80 volts AC, the OCD started tripping. So I didn't reach the full voltage, but you can already see how much bigger the arcs are. So I increased the OCD trip current and set the driver to QCW mode.
It's more QCW looking. Okay, let's turn up the power.
And everything just kind of worked right away. Now you can really see the difference between the QCW arcs and the DRS-STC arcs from before. Doing some measurement, I found that the longest arcs were around 40 centimeters, and to me that was acceptable. Just as a fun experiment, I also tried audio modulation. This works by sending an audio signal instead of a QCW ramp to the driver. It was very loud, but a good proof of concept. I didn't actually explore it that much, but maybe in the future I will. That was not a promise. I think that now is a good time for me to address something. And that is the amount of times that I've said the H-bridge blowing up. And that's not because it's funny. It's because it's a thing that happens a lot when you build Tesla coils. And on one of my runs, my H-bridge also decided to self-destruct. After taking a closer look at the H-bridge, it was pretty clear to me that it was fried real bad. A common failure mode of IGBTs is short-circuiting, and it's pretty clear that that's what happened here. Two of the IGBTs must have short-circuited, and this resulted in so much current flowing through the traces on the PCB that they vaporized into a plasma. I kind of expected this to happen at some point, since I was pushing these IGBTs way past their ratings. I decided that instead of trying to fix this H-bridge, which was kind of honestly just bad, I would design a new H-bridge that was hopefully a lot better. I decided to go with parallel IGBTs so that they could distribute the currents between each other and hopefully be less stressed. I decided to go with 8 IGBTs overall, with 2 in parallel for each switch. In theory, this new H-bridge should be able to tolerate currents of up to 250 amps, but I'm definitely not planning on reaching these currents, so this H-bridge should be bulletproof. The new layout meant that I had to drill and tap a new heatsink. Now, I'm not very good at drilling or tapping, so that went about how I expected. With each IGBT costing about $14 each, for the sake of my bank account, I really wanted this thing to work, so I was extra careful while assembling it. The other improvement that I wanted to make before testing the Tesla coil again was to re-implement the bus circuitry. With the old setup, the maximum voltage it could reach was around 170 volts, but I think that my Tesla coil will operate even better at a higher voltage. This is because at 170 volts in QCW mode, the arcs never really exceeded 100 amps, and I designed my Tesla coil to operate at 140 amps. While this doesn't seem like too much of a difference, because of the way I tuned my Tesla coil, which is kind of too technical and boring for me to get into, it should result in significantly better power transfer and the arcs should be 2 or 3 times longer. So to get a higher bus voltage, I used a voltage doubler circuit that feeds into this bus capacitor. I couldn't use the old bus capacitor because it's only rated for 300 volts, and theoretically I should be able to reach around 350 volts with the new voltage doubler. This thing is rated for 450 volts, and it's also got some extra capacity for good measure. I'm gonna be honest, this thing scares me, like, a lot. Should I see if it's still got charge on it? I know it doesn't. Oh, it does, what the heck? This thing can store a little bit over 600 joules at 350 volts, and that is some energy. I think if there's a short circuit somewhere, it might go mildly nuclear. So there's actually a lot of safety measures behind the scenes to make sure that in the event of something catastrophic going wrong, it won't be too dangerous. Once I had made sure that the voltage doubler was working, I was ready for the moment of truth. I didn't realize how big these arcs were gonna get, so in hindsight, it probably was not the best idea to do this in my bedroom.
Oh my.
So yeah, it works, and it works way better than I ever expected it to. The longest arcs that I measured were around 1.4 meters, and that's just a crazy metric coming from a secondary coil that's only 16 centimeters tall. But then, just after I stopped recording, the driver's fiber optic receiver got stuck receiving an on signal, and this made the driver oscillate for way longer than it was supposed to. This destroyed some of the gate driver ICs and made it stop working. So after only getting to run the Tesla coil for a couple of minutes, I had to replace the fiber optic receiver and the broken gate drive ICs. It turns out there's just a bad solder joint on the fiber optic receiver that disconnected when I tugged on the fiber optic cable by accident, and that was what caused the issue. I was pretty annoyed while replacing the parts on the driver, so once everything was fixed, I was really ready for everything to work and for me to be done with all the problems. So I did a test, and it didn't work.
Oh, that's weird. They're smaller now.
There was this weird chirping noise, and the arcs were really small. I thought that this meant that this was some kind of new failure mode of the H-bridge that I hadn't seen before, so I replaced all 8 IGBTs on the H-bridge, which was an absolute nightmare. I feel like the amount of time it takes to fix all these problems is not well represented in this video, but every time I have to replace a part, it takes 6 days to ship at least, and then it takes another 3 or 4 hours just to find out that the problem is still there, and what you fixed probably didn't fix anything. And I'm going on this rant because once I replaced the IGBTs, nothing changed. So like, I don't even know if the IGBTs were broken. And they probably weren't, because like, IGBTs don't make weird sounds when they're broken, I don't think. So my only idea now on how to fix the problem was to replace the driver. So I did that, and I didn't film anything as kind of a way of silent protest. I mean, that doesn't really make sense thinking about it now, because like the whole point of this project was to make a YouTube video, so like, anyways, I put everything together, and after basically replacing everything, I didn't see how it couldn't work. So, it works again. That's a relief. I went for a higher power test, but before I could get very far, the OCD tripped. I was kind of messing with the setting a lot while I was trying to figure out all the problems, and never set it back to 150 amps. So I turned the OCD knob to where I thought was 150 amps, and then went for another test. So, it stopped working. I couldn't figure out what went wrong and what I did, and then it hit me. I just turned the OCD knob the wrong way, and I set the OCD to 20 amps instead of 150, and it was tripping way before an arc could even break out. So I pranked myself pretty good with that one. The next day, I did a full power run in my living room, because my bedroom was definitely too small last time I ran it. Since the start of this project, it's been about 2 years, and I think that now I can finally say that it's finished. The fact that it works at all is pretty impressive, but the fact that it works so well is just like crazy. Like, I never expected it to work that well. And I've learned so much from this project, but more importantly, guys, I'm actually so done with this thing. Like, and right before I was about to wrap up filming, the IGBTs failed, and I'm definitely not building another H-bridge, so it's done. I'm calling it, like, no more. The biggest hurdle in this project was definitely designing the QCW driver. It took a year on its own before I could even start developing the rest of the Tesla coil. And since there is such a lack of good QCW drivers on the internet, I've decided that I'm going to release the files for the QCW driver so that you can use it to drive your own Tesla coils. And if you're really good at Tesla coiling, maybe you can make it better. The website with all the documentation and files should be in the description. Whoa, I broke the fourth wall, I can see it right there. You should click on it. And if this video has inspired you to start building Tesla coils for the first time, don't start with this one, because it's literally the most difficult Tesla coil to get working. It's like infamous for that. I should also mention that this video is not a tutorial, nor is the website, and I assume no liability for any injuries or destruction of property that comes with you using my Tesla coil driver. I'm just saying, this stuff's dangerous and I don't want to get sued. And if you want to get started with Tesla coils, I would recommend doing lots of research and starting simple with SSTCs and DRSSTCs before moving on to more complex Tesla coils. Because unlike QCWs, these kinds of Tesla coils have tons of great resources. So thanks for watching. Hopefully my next video doesn't take another 2 years to make, but no promises.